Welcome to this video on Moment of Inertia Part 1. In this video, our main goal is to define and come up with a practical definition of what moment of inertia actually is. This is often the most confusing topic for students when they first study rotational motion because they don't really have a very realistic or practical or physical definition of what moment of inertia is. They just know where to plug it in an equation. And so the first time that you throw something, a curveball, it's a very confusing concept to manage. And the main reason for that, as I'm going to show you here, is that a lot of students have an incorrect definition of what mass is. So let's jump in right there. Now you might be thinking, that is not a confusing definition. Mass is the quantity of matter that makes up a particular object or system. Now that definition is not incorrect, but it's not really a good definition when we're talking about motion. This definition, what I'm going to say, is more useful for chemistry or a biology class than it is for a physics class. So I'm going to cross it out, and I'm not saying it's incorrect, I'm just saying it's not the most correct way to talk about mass. In physics, when we're dealing with mechanics or motion, the most important idea here is to see mass as a resistance or a measure of resistance to change in motion. And this is a very important way to look at the concept of mass. So when we're looking at in the context of motion, mass is rather a resistance to the change in motion. So let's take a look at an example here to make this make more sense. Let's say I have this purple box over here, and I have then a blue box. And the blue box has a mass of m2, and the purple box has a mass of m1. And what I'm going to say here is that m1 is much smaller mass than m2. So if I use Newton's second law, which is that the net force is equal to the rate of change of momentum, also known as the mass times acceleration. Let's say that I want to achieve the same acceleration here for both of these objects. So I want to achieve the exact same acceleration for both of these objects. I know that my experience hopefully would tell me that mass 2 offers a lot greater resistance than mass 1 does, which means that if I want to achieve the same acceleration, here I'm going to have to apply less net force than I am on this side in order to achieve the same acceleration. Here I will need to do much more net force than I might need to over here. So we see that mass is really a measure of resistance to change in motion. And when I look at it from that perspective, all I'm concerned with in the factor of mass is that it is the amount that is going to make it proportionally more force required to accelerate something to the same rate. Okay, so that's our definition of mass, resistance to a change in motion. More mass means more force needed to match the acceleration between two objects. Let's jump over to moment of inertia now. First and foremost, I'm going to go ahead and write up the net force analog in rotation, and that's something we've talked about in previous videos. You might check those out if you haven't watched them, and that is that net torque is equal to the moment of inertia, I, times the angular acceleration. So now let's look at two different situations here. Let's say that I have a rod attached at its center, and there's a clay ball on each end of this. Okay. Now in the next situation, kind of comparing these two, I'm going to make another rod of the same length, okay, but now I'm going to say that there's much larger clay balls attached to the end. And what I might see here in this example is that if I wanted to start spinning these, so that, let's keep in mind they're fixed here at their centers, and I push on one side so that I can start to spin this contraption. Over here, I'm going to need to push with a greater force or achieve a greater torque in order to achieve the same angular acceleration. So if we put this up this way, if we say that the angular acceleration here, okay, and the angular acceleration here, I want those to be the same value. So I'm going to say that the angular acceleration in the purple example, we'll call that 1, I want it to be equal to the angular acceleration in situation 2. Now, if I look at it from this perspective, the same idea that I was showing here, I am going to need to use proportionally more torque in order to achieve the same angular acceleration, because this object has greater resistance to the rotational change in motion. So I'm going to define the moment of inertia as the resistance, or a measure of the resistance to a change in angular motion or rotational motion. So here, instead of looking at linear or translational motion, here I'm looking at rotational motion. These are going to be harder to get turning than the purple side. So what's going to have to happen here is that the net torque on situation 1 is going to be less than the net torque required for situation 2, because the moment of inertia of 1 is less than the moment of inertia of 2. So we can see here, in order to achieve the same angular acceleration, so to have these change their speed at the same rates, I would need to push harder on this one, the bigger one, than this one. Now it's not, what we find is that it's not only because of the mass, because you might say, well, yeah, it's just the mass, right? These are small masses, these are large masses, and so you're going to have to push harder again. Let's change the situation slightly. What I'm going to say now is that instead of changing the clay balls on the end, what I'm going to do is I'll keep the apparatus from situation 1 exactly the same, and I'm going to push it so that I can achieve X amount of angular acceleration 1. Now on the left hand side, what I'm going to say is I'm going to use the exact same mass clay balls, but this time what I'm going to do is I'm going to make this rod a lot longer than it was in the previous example. Now we're going to say that the rod's made out of a material that's extremely light compared to the mass of these balls on the ends, and so it's not going to really factor in terms of its mass. When I look at this example here, what I end up finding is that in order to achieve, let me change my color here, in order to achieve alpha 1 being the same as alpha 2, so I want to achieve the same angular acceleration, what's still going to have to happen is that the net torque in situation 1 is going to be less than the net torque in situation 2, and that's because the moment of inertia in situation 1 is still less than the moment of inertia in situation 2. If I told you both of these situations were true, what you would hopefully narrow it down or deduce was that it's not only mass that makes resistance to rotation, but also position from the axis of rotation. So it's not only the mass that's causing a resistance to the change, it's also the position. And therefore, we need to say that not only is M important, but also where M is located relative to the axis of rotation. And we come up with a very generic equation here for a point mass, okay, at some distance from axis of rotation, and we use the generic equation I is equal to mr squared to come up with the moment of inertia for a point mass. Now something that's very important to remember is that in this example, This is just having a point mass, not including the rod that is over here, because its mass is basically insignificant, is what I said, compared to the mass. So for a variety of different shapes, let's say that instead of having the masses located at the ends here, we spread the mass out, so you were basically just rotating a big metal bar where the mass didn't have any specific location, it was spread out over the case of the bar. I can't use this equation in this form anymore, but I can think about this long rod now as being a sum of all the tiny little point masses along the sides. So in the next video, what we're going to do is take a look at how you can calculate the moment of inertia for a system where you have mass that's not just located at one single point at some distance away from the axis of rotation. So the big thing to take home here is that mass is a measure of the resistance to the linear change in motion. So we can add this word now. And that moment of inertia is the resistance to the angular change or the rotational change in motion. Mass is only concerns itself with kilograms, whereas moment of inertia concerns itself with kilograms and the position of those kilograms relative to the axis of rotation.